In this video, we're going to talk about the dot product. So let's start out with the definition. The dot product of two m-dimensional vectors u and v is defined to be the sum u1 v1 plus u2 v2 plus etc. plus um vm. You may also, in other texts, see this called either the inner product or the scalar product. These names are all interchangeable. To see why the dot product is a useful object, we first need to understand some of the properties. So if we have three m-dimensional vectors, u, v, and w, and scalars, s and t, then the dot product is commutative. That means u dot v and v dot u are equal. 2. Compatible with scaling. This means that if I scale the vector u, then take the dot product with v, that's the same thing as scaling the dot product u dot v. And 3. Distributes across linear combinations. This means u dot the linear combination sv plus tw is the sum s times u dot v plus t times u dot w. The proof of each of these is somewhat instructive. The first property is simply a consequence of commutativity of multiplication. So if we write down u dot v, and then we switch the order of multiplication on each of the summands, we see that we get v dotted with u. Compatibility with scaling is similar. It uses the associative property for real numbers. If we write down the dot product of su with v, then we get the product of the components pairwise, su1 times v1 plus dot 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 plus sum vm, and then we associate so that the u's and the v's are together, and we're left with s times u dot v. The third property uses the distributive, associative, and commutative properties of the real numbers. So if we take u and we dot it with the vector sv plus tw, we'll get u1 times sv1 plus tw1 plus etc. plus um times svm plus twm. Now we can distribute the u's across each of these sums. We can group together the terms with u's and v's, as well as the terms with u's and w's. We can factor an s out of the first summation, and we can factor a t out of the second summation. And now we recognize that the first summation is u dot v, and the second summation is u dot w. Before we move on, let's make an observation. If the linear combination is on the left, say sv plus tw dotted with u, the first property tells us that this is equal to u dotted with sv plus tw. The third property tells us that we get s times u dot v plus t times u dot w. And switching the order, we see we get s times v dot u plus t times w dot u. This tells us in general that we can take the dot product of linear combinations the same way we multiply polynomials. So let's say we have c1u1 plus c2u2 dotted with d1v1 plus d2v2. We can distribute the left vector over the addition on the right. Now, we can use the observation above to distribute. So we get c1 d1 times u1 dotted with v1, c2 times d1 times u2 dotted with v1, plus c1 d2 times u1 dotted with v2, plus c2 d2 u2 dotted with v2.